We have Zhouyang Jia who will be speaking first, but let me tell you that we have this new prize stand. So if you haven't yet signed in, you still have 5 minutes to swipe your university ID there. And if you are an eligible person, that is an undergraduate, a graduate student, or a faculty member in computer science, then you are eligible to win a prize at our drawing, which will be in half an hour. And so now let's hear about error handling and bugs.
Yay! Thank you. Thank you for introduction. And today I'd like to share our recent work detecting error handling bugs without error specification equal. This work is recently accepted by Applied Software Engineering Conference. That's a conference. As on the software interacts with its environments or libraries. Example, if we want to open a file, we call open, and the library will send a file on disk. And if there's no such file, it will return none. And next, we need to handle this error or a crash may happen. In this case, you see there is an error handling bug. There are many existing works of detecting error handling bugs. These works typically requires two inputs. The first one is source code. Another is error specification. Here, error specification describes whether a function can fall, and if yes, how the function communicates with its caller. For example, in this case, fopen will return a val pointer on success and return a non pointer on error. So the existing works, the first step of these works is to find the error path.
Excuse me, use the mic.
Okay, thanks. Thank you. The first step is to find the error path. In our example, there are two paths work. The first one is the if statement is error path, the else statement is normal path. So, and the second step is to check if there is a bug in the error path. So this is how existing works works. Okay. However, recurring error specification is non-trivial. On one side, manually generating requires huge human efforts and terminology. On the other side, automated generating is not accurate enough. Although in the stage of artwork, the precision is like 77%. Because this is only the very first step to detect bugs. So every false positive in this step will negatively affect the following analysis. So our design target is to detect error handling bugs without the error specification. To achieve this, we study the real-world source code. Here are some examples like calling the function change root or ch root. In the first two examples, we can say when change root returns -1, they print something. Okay, and these two examples print something when change root doesn't return 0. So since change root can only return two values, -1 or 0, so doesn't return 0, which is basically the same to returns -1. So we can find a pattern that change root is checked by an equivalent condition, which in our example is returning -1, and handled by the same action, which is log in our example. So inspired by these examples, we developed EH minor. The insight is very simple. First, we mine error handling rules from code repository. And the second step is detecting error handling bugs by using these rules. So the difference between error handling rule and error specification might be confusing. An error handling rule is like change root should be logged when returning -1, while an error specification is like change root returns 0 on success and -1 on error. So the fundamental difference is that we do not infer the semantics of -1 or 0. There are two main challenges to implement EH minor. The first is to judge the equivalence of check conditions. Here we have 4 check conditions, and we want to know whether they are equivalent. we found two conditions can be equivalent in 3 levels. The first is syntactic equivalent. You can see it means two conditions are exactly the same, except for some comments or lines. The second level is semantic equivalent, which means these two conditions will always choose the same branch, whatever the function for returns. Okay. The third one is pragmatic equivalent, which means these two conditions are equivalent only when the function, only when the return value of the function for is limited. For example, in our example, if for can only return -1 or 0, these two conditions will be equivalent. That makes sense. Okay. So in our example, the first two check conditions are syntactic equivalent, while the last two are semantic equivalent. The second and third ones are pragmatic equivalent. Okay. We studied these equivalent levels in 5 applications. In each application, we sampled a function and took cosine of that function. We totally have 100 samples in each application. We manually inspect the check condition of each sample. The result is shown in this figure. You can see 26% are syntactic equivalent, while 52 are semantic equivalent, while 14 are pragmatic equivalent, while others are not equivalent at all. And we further select 100 cross-application samples, which means two cosines come from different applications. And in this case, you can see the syntactic equivalent decreases from 26% to 10%, while the pragmatic equivalent increases from 14% to 28%. This result makes sense because developers of different applications may have different coding style. They may use different syntax to implement the same behavior. Okay. The second challenge is to extract handling actions behind some program-specific functions. So here in our example, we have 4 code snaps used for different functions to perform log. Okay, we need to know the action that behind these functions. To achieve this, we study how developers handle errors in real-world applications. In each application, we sample a function and one cosine of that function. Then we manually inspect its error handling code. We find the handling code can be generally classified into 2 types. One is to use unconditional branch keywords like return, break, continue, or go to. The other is to use program-specific functions to perform some error handling actions like log, exit, close, free, or delete. The distributions of these keywords or actions are shown in this figure. You can see in most cases, developers prefer to use return, log, or exit. Okay. To mine error handling rules, we first transfer the source code into structured data instances. After that, we normalize these instances for ease of comparison. And finally, we can mine error handling rules from these normalized instances. Okay. First, to generate structured data instances, first we need to search for, the first step is to search for library function calls. So in this example, we got the function full. This is, sorry. Then we search for check conditions which are flow dependent on the library function call. So here we have 2 if statements and 1 else statements. Here we see A is flow dependent on B. We mean A reads some variables which are written by B. Okay. The third step is to search for functions or keywords which are control dependent on the check conditions. So finally, for this, in this example, we can get 4 data instances. Okay, the next step is to normalize these instances. As we can see, each instance includes 3 elements. The first is the function name, and the second is check conditions. And we need to judge the equivalence of these check conditions. The third is handling actions or keywords, and handling functions or keywords. And for functions, we need to extract their actions behind this function. Now we normalize the check conditions. Suppose we have 2 check conditions, A and B. And in this example, we can see that every X that satisfies A will also satisfy B. Okay, or we can say A implies B. This statement is exactly the same to another statement, which is no X that satisfies A but does not satisfy B. If we formulate this sentence, it will be A and not B is unsatisfiable. So basically, if A implies B, then we know A and not B is unsatisfiable. So here is how each manner judges the equivalence. If A and B are equivalent, then we know A implies B and B implies A. Then A and not B is unsatisfiable, and not A and B is unsatisfiable. So here we transfer the equivalence problem into a satisfiability problem, which can be which can be solved by a SMT solver. And finally, equivalent conditions will be attached the same mark in the data instances for normalization purpose. Okay, then we normalize the handling functions. Here is an example of logging function from my circle print arrow. You can see this function calls another function named arrow log print, which further calls print buffer to file, which finally calls fprintf. If we see this call chain, we can find 2 heuristic rules. The first is the handling functions always wrap certain library functions. For example, like library function printf or fprintf for log, because if you want to print something, you have to call the fprintf family. And the second rule is in the call chain, each node contains certain keywords related to the action. For example, the keyword log or print for log action. So based on these rules, here is how each manner extracts actions. First, we predefine a library function list and a keyword list for each action. Then we build call graph of the handling function. After that, for each path in the call graph and each action in this site, we check if the path performs the action according to above rules we just mentioned about. According to these 2 rules. Okay. And finally, the handling functions will be replaced by its action, if any, for normalization purpose. We implement each manner based on climb for front-end analysis, VMIR for data flow analysis, Z3 for SMT solving, and SQLite for data management. And our code repository includes 117 C or C++ applications from 15 software domains. This is our code repository, many applications. So we evaluate our tool in the code repository, and each manner mined 1,036 rules from these applications, and we further detected 2,266 violations, while the precision is about 88%.
What is a violation?
I mean, violation of the rules. So here we have some error handling rules, right? And if next we need to find violations of these rules in source code. So one violation is kind of a potential bug.
Can you give me a quick example of what is a violation? Just a simple example.
Okay. For example, if we have a row, change row should be logged when returning -1. And in the source code, you write something, you call the change rows, but you didn't check the return value. I mean, if the function is returning -1 and you didn't perform any handling action.
So if the call to change root doesn't look at the return value, that's a violation.
Yeah, you don't follow this rule, it's a violation.
Okay.
Okay.
Thanks.
Okay. So, and finally, we report 142 bugs. Among them, 106 are confirmed and fixed, as shown in this table. There are six bugs that are rejected. We also evaluate our tool in Linux kernel to evaluate whether the tool can be running in different data sets. So in Linux kernel, we mine 1,590 rows and detect 2,069 violations, while the precision is about 83. So, and we finally report 68 bugs. Among them, 42 are confirmed or fixed, others are rejected. We also compare our tool to existing tools which are using error handling rules. Here we have three advantages of using error handling rules. First, we have here accuracy. Because each miner does not have to infer the semantics of API return values, this feature improves about 17% based on the state of R2. The second is better scalability. Each miner use lightweighted constraint solving, which make it about 20 times faster than the state of R2. The third one is easier to repair because we can get error handling actions besides the error specification. With the help of these actions, we manually generate and report 210 patches, although we have limited terminology. Okay, and that's it.
So, I don't know how related my question would be, but at some point I had a discussion with very experienced computer scientists in the context of what is better for software to do, to kind of handle an error or just to crash. And the answer was it's better to crash. And I was really shocked firstly, but later I accept that preference of crashing if instead of continuing with wrong state. Do you have any comments on that? Maybe just somebody would do you need a...
You mean how to handle errors?
No, what in your opinion is better? If we are getting to undefined state, is it to error handle it or to crash?
From the point of user, of course, they never want to say the software crash or something. So it will influence the user experience, right? So I think the software would be better if we can handle this error properly instead of letting it crash.
Are you saying you believe that for all types of applications or for certain specific?
Well, the question all, ever, never, reject that type of yes,
So I like your talk, thank you very much. Back, I thought it was interesting how you had the breakout of the syntactic, the semantic, and the pragmatic. And I'm wondering if you all did any analysis of the different errors that were present in the various different open source products that you use. And the reason that I say that is, and I know that our she won't be surprised that I'm going to go on this tangent because this is one of my PhD advisor's favorite topics was the semantic fault model, okay? And the fact that these bugs instead of putting X less than Y, we accidentally put X greater than Y. Oh, almost every input that you give will cause the crash, as Dr. Jia was saying. But I'm just wondering, because as you go through and you're using all these different programs that are available to help you with your EH minor, you're forced to use what they have, right? You have to use the bugs that are there. You have to use what they have. So I'm just curious, because it could be the case that you're across these different applications, some of them have, I don't know, all semantically large faults, and some of them have all semantically small faults. And so for me, I would be curious to know if that impacts how your EH minor performs. Does that make sense? Or maybe I'm way out in the field. I don't know. But I'm looking at. I know it's a good question. It's probably more of a question to your advisor. But I'm looking at this. Okay, equal to minus, not equal to 0. Da, da, da. And I just, in my mind, I'm saying, yeah, but if it's supposed to be not equal to
Or
1.
maybe greater than something, or
Yeah, but right. That's.
it's okay. It's okay because we use the XML solver, so it can handle it.
It's kind of like a static approach. I mean, they actually take into consideration all the possible inputs by formulating semantic as certain constraints. So you use the certifiable solver that rather than instead of actually executing.
Right. Okay, but then when you go in and you restate this, and you do the A and not B, and not A and B, right? This is when right before you're going to go to your solver, right? So in other words, this is abstracted level. So what the condition A is just abstracts that level away.
Oh,
Do you see what I'm saying? So I understand what you're saying, but what I'm saying is, I don't know. I mean, maybe it's going to perform differently based on the distribution of those types of conditions.
Yes.
Are you with me?
Yes. Here can be handled like both type or inputs. Right.
So I just wanted to clarify, you're talking about the state of the art, and you're comparing what you've made to the state of the art. And just, is the state of the art in this case a program which is given a set of rules, like change root should log when if it returns this value, and then the program goes and finds all the cases where that rule isn't matched. And is that the state of the art is?
So
Sorry.
evaluate the state of the art.
What is the state of the art program and what does it do?
The state.
State of the art.
State art. And the state art program. As you can see in this slide, the state of art display the curse this our specification, and with this information we can we know what is right and what is Yes. Because the error security is only the very first step to detect bugs. And after that, you need to find the error path. They made mistakes in this network. So there.
So you can be 100% accurate in the first step, but then when you go to find the error path, that might be where,
Yeah.
okay.
Now, this, of course, has led to you encountering a whole lot of code with a whole lot of bugs. This is a sort of side question, but has this given you any kind of opinion that maybe there should be fewer ways to check these error codes rather than, having all these semantically equivalent, syntactically equivalent? Would it lead you to wanting the options that somebody has for checking that something has gone wrong to be more constrained so that these bugs are introduced less often? Just kind of an opinion question.
The reason that these bugs happen is that most developers just focus on the function code instead of this non-function code. So, and
What you're asking for is a standardization of style.
Yeah.
And yeah, if the style were standard, it would be easier to find mistakes. If the style is never going to be standard, you've got to look for mistakes. Other questions? I was struck by how often GoTo was used as the solution. That's really surprising because typically GoTo is not a good answer. But look, 6% of the time, GoTo is in the in Emacs, in MySQL.
13% in MySQL.
it is C. Actually, in some programs like the Linux kernel, GoTo is used very frequently.
That's true. It's used to always go to error cases.
Yes,
That's right.
errors.
So it's not just GoTo. It's GoTo, and then what it goes to is the standard error handling code.
Again.
So calling it GoTo is maybe not fair.
There was another question back here.
Yeah. Another question.
I was going to ask if the CH monitor could also be used to find exploits in the code. If you could use the EH monitor to find exploits in the program.
To find a way to attack the program.
I don't think so. Yes, because this is only kind of code quality. Something that the developer just forgot to write some other code, and we can handle this.
Well, thank you very much. An interesting talk.